Okay guys, we're back with video number 2 on chapter 9. So this is Chem4, week number 9, video number 2. Alright, so we are continuing with solutions, and I just want to mention here a little bit about the past video, video number 1. It says, we've already mentioned, or we've already talked about solutions. We've introduced what solutions were and the effect of temperature on solubility. Remember, I had that little chart, and I said that as the temperature gets turned up, you can dissolve more solutes in a given amount of solvent, and that given amount of solvent, I believe, was 100 grams of water, which is the same thing as 100 milliliters of water. Now I want to talk about not temperature, but pressure. So the effect of pressure on solubility. Right away we can rule two things out, and that's that pressure has no effect on the solubility of a liquid or a solid. Why is that? Liquids and solids are already compressed to the point where more pressure isn't going to affect how much liquid or solid you can dissolve. Now, gases, on the other hand, are very, very non-compressed, if you will. They take up the volume of the entire container, so pressure effects on gases are big, and that's where we talk about Henry's law. So Henry's law, this is discussed in your book as well. It says the solubility or concentration of a gas dissolved in a liquid is directly related to the partial pressure of that gas over the liquid. So here's what I mean by that statement. I'm drawing a sealed container, and you will see that you have dissolved gas particles below the surface and some undissolved gas particles floating in the air. Now the undissolved gas particles floating in the air, they are condensing into the liquid at the same rate the liquid is naturally evaporating. So we're at equilibrium. Now if I increase the pressure, right, what am I doing? I'm increasing the pressure. I'm coming down on the surface of that liquid. I'm forcing more gas particles to dissolve into the liquid. So if you see, I've got less gas particles in the gas phase, more gas particles actually dissolved into the water solvent. So yes, I'm referring to them as gas in both situations, but above the surface they're actually gas particles. Below the surface it's dissolved gas, kind of like CO2 in a can of Coke, carbon dioxide, the fizz. So as my pressure goes up, more gas molecules are entering the solution than are leaving it. I got more down arrows in picture number 2 than I do evaporation arrows. Now, eventually, after we've increased that pressure, over time, the amount of dissolved gas particles are going to catch up, and they're going to start to evaporate, and we're going to get the condensation and evaporation rates being the same again. And this is a new equilibrium is reached, this time with more dissolved gas solute particles. All right, let's move to the top of our next page of notes. So, as P gas, now P gas is the pressure of the gas over its liquid. That last drawing, right, I had a sealed container, I had a liquid level, and gas particles were above the liquid. That's what the partial pressure of the gas is. It's the measure of the pressure above the liquid. So that is called vapor pressure. So as P gas increases, so does the concentration of dissolved gas particles. It's kind of like shoving more gas particles into the liquid to dissolve them, and we use pressure to do that. Okay, it looked like a piston going down on the last page. So Henry's law says that the concentration of gas 1 divided by the pressure of gas 1 is equal to the concentration of gas, it's situation 2 divided by the partial pressure of the new situation 2. C1 over P gas 1 equals C2 over P gas 2. This is Henry's law. All right, the best way to do this is with examples. Examples are always help clarify things. So at 20 degrees Celsius and the partial pressure of 760 millimeters mercury, the solubility of CO2 in water is 0.169 grams per 100 mils of water. What's its solubility in water at a pressure of 2.5 times 10 to the 4th millimeters mercury? Much larger pressure, we're expecting a much higher concentration, in other words, a much higher solubility. C1 over P1 equals C2 over P2. So I set up my equation here. I can clean up my numerators by just dropping the per 100 milliliters. And I get 0.169 over 760 equals X over 2.5 times 10 to the fourth. I can cross multiply and set them equal, and I can solve. And when I do that, I figure out I can now dissolve 5.6 grams of CO2 in 100 mils of water. That's a lot higher than 0.169. If I increase the pressure on a gas over its liquid, you can dissolve more gas particles in the liquid. This is how a can of Coke works. All right, totally separate topic now. At the top of the page, I want to talk about units of concentration. We're going to talk about molarity and mass percent. Today we'll talk about molarity. Very beginning of video number 3 coming up, we'll talk about mass percent. So molarity we're going to get to. Molarity and mass percent are very specific. What I'm beginning with here is very general, and that is the following. Dilute and concentrated. They don't tell us anything about numbers. They're just relative terms, and they're not exact at all. Okay? So units of concentration. The terms dilute and concentrated we use in everyday life, but they don't tell us specific numbers. A solution's exact concentration, however, can be expressed in several ways. We're going to learn 2. Today we'll learn molarity. Okay? Molarity is the most popular. I think mass percent's a close second, and that's in the next video. Molarity, big M, capital M, is the moles of solute divided by liters of solution. So it's the moles of what gets dissolved, the solute, divided by liters of the solution. And the solution is both solute and solvent. So 1 molar, 1 big M, is the same thing as a mole/liter. Okay? 1 molar is 1 mole per liter. That's important when we do our calculations. Examples. Examples help. Calculate the molarity of a solution containing 50.0 grams of vitamin B1, and I've given you the molecular weight of 337 grams per mole. So calculate the molarity of a solution containing 50.0 grams in 160 milliliters of solution. So molarity, big M, is equal to moles per liter. All right? So if I want to find the molarity, I have to find moles and I have to find liters and then put them together. So 50.0 grams of vitamin B1, if I divide by the molar mass, that puts me in moles, 0.148 moles of vitamin B1. Now, it says 160 milliliters of solution, but I want liters, moles per liter, 0.160 liters. 0.148 moles of B1 divided by 0.160 liters equals 0.927 moles per liter, which I'm going to call 0.93 molar, just to stay within my significant figures. Next question. Top of the page says, how many moles of solute are present in the following 2 equations? So not 2 equations, but the 2, I have an A and a B here. How many moles of solute are present in the following? A, 125 milliliters of 0.25 molar NaNO3. So I want moles, right? How am I going to get moles? Well, let's start by writing the generality. Molar, big M, is equal to a mole per liter. That means 0.25 equals X over 0.125. If I cross multiply and set them equal, I can put a little 1 underneath the 0.25, and I get a value for X of 0.031 moles NaNO3. Okay? B, 450 milliliters of 1.5 molar HNO3. All right, well, molarity, M, is equal to mole per liter. So 1.5 equals whatever moles divided by 0.450. This is just like the one I've just done. So cross multiply and set them equal. You got 2 sig figs, so the answer is 0.68 moles of HNO3. Notice how I don't just write 0.031 or 0.68. I write the units out. Moles NaNO3, 0.68 moles HNO3. All right, next example. The concentration of C27H46O cholesterol in blood is 5.0 millimolar. Okay, that's kind of like a milligram or a milliliter. It's a millimolar. The concentration of C27H46O in blood is 5.0 millimolar. how many grams of it are in 250 milliliters of blood? Well, right away I'd change 250 milliliters to 0.250 liters. You don't do that all the time, but you do when you're talking about molarity. All right, so start with what you're given, put over 1, 5.0 millimolar, and then I went ahead and converted that. Now at the top of our next page of notes, I've taken the answer to that conversion. So instead of having 5.0 millimolar, I like 0.0050 molar, and that's equal to X moles divided by 0.250 liters. You can see why it was important to convert milliliters to liters now, right? So you solve for X by cross multiplying and setting them equal, right? You can put a 1 underneath 0.0050 if it makes you feel better. And then X is 1.3 times 10 to the minus 3 moles. But I don't want moles, okay? I want grams, all right? So what have I done here? I start with what I'm given, put it over 1, 1.3 times 10 to the minus 3 moles, C27H46O, multiplied by the molar mass of 386 grams. 386 grams is 27 carbons, 46 hydrogens, 1 oxygen on the periodic table, and I get an answer of 0.502 grams, C27H46O. I'm missing the little G there after 0.502 grams. Okay, next example. What mass of calcium carbonate, CaCO3, is needed to react with 75 milliliters of 0.10 molar HCl according to the following balanced equation? So the balanced equation is already done for us, okay, and I want to find out what mass of calcium carbonate do I need. So I put a little XG there just so I kind of know where I'm heading. And all the information they've given me is for the hydrochloric acid, so I'm going to work with that. Well, I know that in order to bounce over to CaCO3, I'm probably going to need mole ratios, right? We've learned this when we talked about stoichiometry. So I need to find out how many moles of hydrochloric acid I do. To do that, I know that 0.10 molar is equal to X moles over 0.075. You do the math, you get 0.0075 moles HCl. Start with what you're given, put over 1. In the balanced equation, there are 2 moles of HCl for every 1 mole of CaCO3. That puts me in moles of CaCO3. If I multiply by the molar mass of CaCO3, I get an answer of 0.38 grams CaCO3 as my answer. Okay, so it says what mass of CaCO3? So I target in on CaCO3, yes, but you can only jump from hydrochloric acid to CaCO3 in the balanced equation when you're doing mole ratios. So hopefully that helps, and then the next video talks about mass percent, dilutions, and then also some sample problems.